Hi, everybody. My name is Ufuk Topcu, and I'm from the University of Texas at Austin. I will discuss my study on runtime enforcers in adversarial and information-limited environments, which is essentially looking into synthesis of enforcers for systems that interact with adversarial environments or attackers. To put this into a more concrete context, let me start with a use case that builds on the concept of attack graphs, which are essentially finite state representations of possible penetration scenarios or the launch of multi-stage attacks in computer networks. The concept is not necessarily new, but there is a renowned interest in this, especially focusing on automated construction of such attack graphs and in a scalable manner by exploiting the underlying modularity. Once we have such a representation, the next issue is how we can model the interactions between the system and its adversarial environment. And this decision requires looking into a series of questions. For example, what are the actors? How do they interact? Whether we know enough about their interactions so that we can end up having a deterministic representation of such interactions, or do we have to deal with non-deterministic or stochastic uncertainties in the transitions? Do we know the underlying graph? Or does the system or the adversary itself know enough about, the transition probabilities that determines the evolution through the system? Or does the system or the adversary can know enough at runtime about the other side or about its own state? Or what resources do they have? For example, do they have enough memory? Can they keep enough information in their memory to reason about in their interactions? It is very likely that a single model is not going to be appropriate for all concerns that we might have to deal with. And therefore, it is pragmatic to look into a hierarchy of models. One that I have kept in mind throughout the study is at the bottom, we have so-called Markov decision processes. And depending on what kind of complications we deal with, it is going to branch out. For example, if we introduce an adversary, we probably will need to deal with two-player stochastic games, limitations in runtime information. We will likely have to deal with partially observable Markov decision processes. If we don't know enough about the underlying interactions, for example, if we don't know the transition probabilities, we will likely deal with so-called uncertain Markov decision processes. And these complications can interleave. For example, we might have partial information stochastic games on one side and uncertain partially observable Markov decision processes on the other side, and it just can climb up in the hierarchy, increasing the resulting complexity. So with the modeling question, I just commented on the modeling issue. Now let me move on to the concept of shields and shield synthesis for runtime enforcement. Conventionally, if you want to reason about whether a system is going to satisfy its safety or correctness specifications, we would resort to verification, whether the system satisfies the given specifications. But such an approach has its own limitations in, for example, scalability, because it takes a finely granular view into the system representation. Whereas the shielding takes a little bit higher view because it gets to modify the system's output in such a way that even if the input-output relationships without the shield does not satisfy the given specifications, the objective is to get the input and the modified output of the system, modified by the shield, satisfying the specifications. And it would be trivial if we could actually overwrite every single output of the system, but that would defeat the purpose of the underlying system at first place. Therefore, the shielding process has to satisfy certain properties. One of them is being minimally interfering. Whenever it should interfere only whenever absolutely necessary, and then it should delegate the authority back to the system as soon as possible. And it turns out that we can actually synthesize such shields from specifications only, and it makes us, this process, agnostic to the inner workings of the system. That means that even if the system has a very complicated inner working, since the synthesis of the shields relies on the specifications, it can actually ignore the underlying complexity. But obviously, it has to be receptive to the properties and needs of the underlying system. Some of those properties are listed here. Case stabilizing, for example, refers to that. if the faults that the shield has to deal with are far apart from each other, then it should be able to guarantee that the input to the modified output relationship satisfies the specifications. I'm not going to go into the detail of that list. In any case, this is the rough description of the shielding idea and how it can be synthesized. The next question, which is very relevant for our context, is how can we do these things, whether we can do these things under information limitations. And it turns out that the key ideas, for example, permissiveness and permissive strategies that give rise to shields, carries over to this context where we have information limitations. On the other hand, at a cost of an added complexity, computational and conceptual complexity. For example, the shields now may not have access to the underlying state or may not know everything about the model, and it needs to fill these gaps. And this gave rise to some recent work on scaling up the synthesis in partial observable Markov decision processes, and actually so-called uncertain partial observable Markov decision processes, where we have a family of models, transition functions. We don't know which one is the correct one. And we want to be able to synthesize a strategy sigma such that when implemented on the actual system, the specifications will be satisfied regardless of which transition function it is chosen from the given family of transition functions. So this uncertainty on the transition functions represents the lack of a prior knowledge, whereas the partial observability models the lack of or limitations in the runtime information. It turns out that synthesis in partial observable Markov decision process is extremely hard. It cannot be overemphasized, and obviously in uncertain versions of these things, uncertain ambiguity is even harder. But interestingly, there has been quite a bit of progress recently, partly in my work, that we can now scale these things up. In particular, we can synthesize relatively expressive so-called finite memory strategies for uncertain partial observable Markov decision processes and accomplish orders of magnitude improvement in scalability, which I characterize as we can now synthesize strategies not only for toy instances of these problems, but relatively large scale and practically interesting and relevant instances. And this scalability was just through ideas in the intersection of probabilistic formal verification and convex optimization. And I believe a pragmatic future direction is trying to make better connections or stronger connections between shielding for runtime enforcement for security purposes or for dealing with adversaries, and these recent progress in synthesizing strategies under information limitations. So this is the end of my talk, and thank you very much for your interest.